You just finished a unit on energy. Energy is what runs our universe. For example, the energy that the Earth uses is almost solely from the sun. And believe me, the sun has an awful lot of energy. If you don't believe me, check out this video clip. You wouldn't want your hand to get in the way of that. But that brings up our next question. In other words, the sun is our source of energy, but that energy is getting to us here on Earth. So the question is, how did the energy get from the sun to the Earth? Well, from your ideas, from your studies in conservation of momentum and in energy so far, we've already seen one way that energy could get from one place to another, and that's directly. For example, if I take this baseball and throw it to somebody else, the receiver will feel the energy that's given off by the ball's motion when it's received. So in other words, when I throw the baseball, I felt that ball hit my hand. Obviously the ball transferred energy to my hand. So this is our first way of transferring energy from point A to point B, and that is moving stuff from point A to point B. When an object moves from point A to point B, it carries its kinetic energy, 1/2 mv squared, from point A to point B directly. It also would carry its rotational kinetic energy. This is called a particle model of energy transfer. We're fairly familiar with the particle model of energy transfer. After all, that's really what we've been doing all along in studying the motion of objects. But there is one other way to carry energy from one point to another that we haven't talked about yet. And that's what this unit's going to be all about. There's a rope on the ground. This coil of rope here. And we're going to do a little bit of a mental experiment. I'm going to take one end of the rope for myself, and I'm going to toss you the other end of the rope. Ready to catch it? Good catch. Tug your end of the rope, and I have my end, and let's make it fairly taut so we can feel each other on the other end. You ready? Now, I'm going to take this end of my rope right here, and I'm going to take this spray paint and spray it. This is red spray paint. Now I'm going to grab that wet paint and the rope. You're still holding on to your end. You ready? Now, if you feel something, that must mean that energy is transferred to you. So you're ready to go? Did you feel that? Now, look at your hand. Do you have red paint on your hand? I have red paint on my hand. But you don't have red paint on your hand. So you received something, you felt something, you received energy, and yet the stuff that I moved didn't make it all the way to you. So we transferred energy without transferring the particle, without transferring the stuff. That type of energy transfer that you just felt was through a whole different type of mechanism. And that type of mechanism is called a wave. Now you may be saying, hey, Mr. Bepke really doesn't have red paint on his hand, and I don't buy this little thing that he did with the rope. So if you don't buy any of that, check out this video clip.
The energy is carried down the alley by the traveling pulse and knocks down the bowling pin.
As you saw the bowling pin get knocked over, you realized that energy did go from point A to point B through the pulse, through the wave, and that the slinky, the end of the slinky that was pulled at one side, did not actually make it down there to the other side. So we have to create a new model for transferring energy from one place to another. It is a wave model. Again, we have two ways of transferring energy, two models that we've developed for transferring energy from one place to another. The first model that we already are fairly familiar with is the idea that stuff, particles or objects, can move from point A to point B and carry kinetic energy with them, both rotational and translational kinetic energy with them. A new model, a wave model, that we're just starting to discuss, and that's what this unit is about, the stuff doesn't go from point A to point B. Only the energy goes from point A to point B. How does that happen?
Here, red dye is used to show that individual portions of the water do not move in the direction the water waves travel.
Now we know that waves transfer energy from one place to another, but we don't know how waves are created and how they actually get energy from one place to another. So let's take a look at this video clip.
The wave moving out from a stationary source travels equally in all directions.
As you saw in the ripple tank, when the water was tapped, a wave propagated outward. I just said the word propagate. You see, particles move, but to differentiate between these two energy models, we use a different term for waves. We don't say that waves move, we say that waves propagate. When the ripple tank was tapped and the wave propagated outward, that tap disturbed the water. You've seen two examples of waves so far, actually three. Our rope example, the slinky knocking over the bowling pin, and also the water being disturbed. In all three cases, we had something, the rope, slinky, and ripple tank or water, and that something was disturbed. Note, by disturbed, I mean it was taken out of its original position, moved in some way. The thing that is being disturbed, the rope, the slinky, the water, is in wave terminology what we call a medium. A medium is the thing that the wave propagates through. The medium carries the wave from point A to point B after the medium is disturbed. So a wave is created by disturbing a medium and having that medium react and carry that disturbance, which is known as propagation, carry that disturbance from one point in the medium to another point in the medium. At this time, we don't want to get into too many details. We just want to get you started with this new concept of a wave. But there are four general categories for waves, and I think you ought to know a little bit about those four general categories before you proceed and start learning more. Let's look at slinkies again, and you'll see in this first video example that by disturbing a slinky once, we can cause what is known as a pulse. A pulse is a wave that is only generated by a single disturbance. We can continually disturb a medium. Again, we're going to look at another slinky. We can continually disturb a medium and displace the medium at one place. And that continuous disturbance will cause a continuous wave. Check this out. So we have two types of disturbances. A pulse or a continuous disturbance called a continuous wave. There are also two types of disturbances as far as pushing and pulling. We can disturb a medium by pushing and pulling on it perpendicular to it, and that's called a transverse wave. That causes a transverse wave. Or we can disturb a medium by pushing and pulling on the medium in line with the medium, and that causes what's called a longitudinal wave. You've already seen a few examples with the slinkies that are transverse examples. The last continuous wave you saw was a transverse disturbance. You pull a slinky from one side to another continuously. The slinky's in this direction. And yet, we pushed and pulled the slinky up and down to cause a disturbance, which caused a continuous wave this way. So the disturbance was caused perpendicular, 90 degrees, to the way that the slinky was running. And again, this is a transverse wave. We can also create waves on a slinky by, instead of pulling them up and down and making a transverse wave, we can push and pull on the slinky this way and create waves. Check out these waves. These are longitudinal waves.
Notice the different parts of a longitudinal wave. Rarefaction is where the individual coils are far apart, and compression is where the coils are close together.
With our longitudinal waves, we took the slinky and we pushed and pulled on the slinky in the same direction that the slinky was going. And so the push and the pull are in line. The force that causes disturbance, the push and pull that causes disturbance, are in line with the medium. And that causes a longitudinal wave. Again, energy is what powers the Earth and the universe. So it's pretty important to know how energy goes from one place to another. And now you've seen that there are two models to show how energy goes from one point to another. We're going to focus on waves, since you already have a pretty good experience with particles and how they move and interact. We just started to catch some of the ideas that are going to be in this next unit, and we hope you enjoy riding the wave for the rest of the journey.